Welcome to this last lecture in our course Analysis of a Complex Kind. Today we'll study the prime number theorem and how it is related to the Riemann hypothesis and to the Riemann zeta function. Complex analysis is an extremely powerful field. This is demonstrated in many different ways, but today I want to show you how it is demonstrated, for example, by the ability to prove a deep theorem in number theory, namely the prime number theorem, using complex analysis. The prime number theorem has in fact first been proved using complex analysis. Nowadays there are other proofs that are known that don't use complex analysis, but the first and most important proof of the prime number theorem is from complex analysis. We'll describe this in more detail in this final lecture. To tell you what the prime number theorem says, let pi of x be the number of primes less than or equal to x. This is called the prime counting function. It counts how many prime numbers there are less than or equal to a number x. So for example, pi of 1 is equal to 0 because there are no prime numbers less than or equal to 1. Pi of 2 is 1 because there's a prime number 2, and that's the only prime number less than or equal to 2. Pi of 3 is 2 because 2 and 3 are prime numbers less than or equal to 3. Pi of 4 is still 2, it's the same two prime numbers that we're counting. Pi of 5 is 3 because we're counting an additional prime number. Now we have 2, 3, and 5 that we're counting. Pi of 6 is also 3 because 2, 3, and 5 are the only prime numbers less than or equal to 6, whereas pi of 7 through pi of 10 are 4 because now I'm counting the prime numbers 2, 3, 5, and 7, and so forth. So pi of 11 and pi of 12 is 5, and so forth. So that's a function that seems pretty random if you look at its values, 0, 1, 2, 2, 3, 3, 4, 5. It seems impossible to find an explicit formula for pi of x. One therefore studies the asymptotic behavior of pi of x as x becomes very large. So for example, one wants to know how many prime numbers are there roughly that are less than 1,000,000. And so an asymptotic formula for pi of x is what one is looking for. The prime number theorem says that pi of x is asymptotically x divided by the logarithm of x. That symbol, this asymptotic symbol right here, means that the quotient of these two sides, namely pi of x divided by x over ln x, goes to 1 as x goes to infinity. You could also write this as pi of x times the reciprocal of that quotient, so times ln x over x. So that goes to 1 as x goes to infinity. Here's a brief history of this prime number theorem and its proof. Euler was the first one to discover the connection between the zeta function, zeta of s, for real values of s, and the distribution of prime numbers. Euler did not look at the zeta function the way later on Riemann did for complex values of s. He looked at it for real values of s and discovered its relation to the distribution of prime numbers, and we'll look at that in a little bit. 60 years after Euler, Legendre and Gauss conjectured the prime number theorem after numerical calculations had led them to believe it should be true. Another 60 years later, Chebyshev showed that there are constants a and b, such that pi of x is bounded above by b times x over ln x and bounded below by a times x over ln x. This does not give you the prime number theorem yet, but it's closer. It's a step closer to the prime number theorem. In 1859, Bernhard Riemann published his seminal paper on the number of primes less than a given magnitude. In that paper, he constructed the analytic continuation of the zeta function that we spoke about last class and introduced revolutionary ideas connecting the zeros of the zeta function to the distribution of prime numbers. Hadamard and de la Vallée-Poussin used these ideas of Riemann's independently and proved the prime number theorem in 1896. The main step in their proofs is to establish that the zeta function has no zeros on the line where the real part of s is equal to 1. Remember, the zeta function has these zeros at -2, -4, -6, those are so-called trivial zeros. And it is unknown what happens in this strip. The Riemann hypothesis says that they're all where real part of s is equal to 1/2, but it is unknown whether there are extra zeros in this strip. And both Hadamard and de la Vallée-Poussin were able to show that there are no zeros on the line where the real part of s is equal to 1, and that enabled them to prove the prime number theorem. So how is the zeta function related to prime numbers? Euler discovered that zeta of s can be written as a product, an infinite product over all prime numbers of 1 divided by 1 minus p to the minus s. Let me remind you how the zeta function was defined. Zeta of s was the sum, and from 1 to infinity, of 1 over n to the s. And we first looked at that for s greater than 1, then we saw we could also do this for real part of s greater than 1, and Riemann was able to extend this zeta function to an analytic function in the entire complex plane with the exception of that point 1. So why is this summation formula the same as this product formula? Here is why this is true. Here again is the zeta function. It's 1 over 1 to the s plus 1 over 2 to the s plus 1 over 3 to the s, and so forth. You could factor this zeta function by the prime factorization s. 1 plus 1 over 2 to the s plus 1 over 4 to the s. So in this first set of parentheses, you'll see all the powers of 1 over 2. So 1 over 2 to the s, actually. 1 over 2, 1/4, 1/8, 1/16. In the next pair of parentheses, you'll see all the powers of 1/3. In the next one is the powers of 1/5, and so forth. This is an infinite product, and if I multiply through, I get the 1 over 1 to the s term by just picking the 1 from each set of parentheses. I get the 1 over 2 to the s term by picking the 1 over 2 to the s from the first set of parentheses and the 1 from all the others. I get the 1 over 3 to the s term by picking the 1 in the first set, the 1 over 3 to the s in the next one, otherwise all 1s. I get the 1 over 4 to the s by picking this 1 over 4 to the s term, and otherwise all 1s, and so forth. Let me just demonstrate the 1 over 6 to the s term. I get that by taking the 1 over 2 to the s and the 1 over 3 to the s, and otherwise all the 1 terms again. So each term is accounted for, and I can't get any additional terms because all I'm doing is, when I multiply through here from these products, I'm going to get a certain number to the power s, and all these numbers occur by the uniqueness of the prime factorization. I don't get any terms twice. Therefore, zeta of s is equal to this infinite product, and in each parenthesis, I see a prime number to the power s raised to all possible powers k. So the sum from k equals 0 to infinity of 1 over p to the ks. Now what does that equal? How can I simplify this? What is the sum k from 0 to infinity, 1 over p to the ks? Let me rewrite that a little bit. I can rewrite that as the sum k from 0 to infinity of p to the minus s to the k. P is fixed, s is fixed. P to the minus s, p is a prime number, s is a number at least 1. So p to the minus s is something that is less than 1. Therefore, this forms a geometric series, and I know this series converges. The value of the series is 1 over 1 minus the term whose powers we're adding, namely p to the minus s. Using that, I find that zeta of s is equal to the infinite product over all primes of 1 over 1 minus 1 over p to the s, which is the same as 1 over 1 minus p to the minus s. That's the way we wrote it up top. So here's again the formula for the zeta function. Once you have this product formula, it is easy to see that zeta of s does not have any zeros for a real part of s greater than 1. So here's 1. And so far we had the summation formula, and there it was unclear whether something could add up to 0. But here's a product. The product can only be 0 if one of the factors is 0. None of these factors are 0, and that shows us that the zeta function is never equal to 0 for a real part of s greater than 1. Now the key step in the proof of the prime number theorem is to show that zeta has no zeros on this line, where the real part of s is equal to 1. The details of that proof go beyond the scope of this course. However, that is the main step. Once that is established, the prime number theorem follows. The prime number theorem says that pi of x is asymptotically the same as x over ln x, meaning again that the quotient of these two quantities goes to 1 as x goes to infinity. But it doesn't say anything about the difference of the two sides, so pi of x minus x over ln x. The prime number theorem doesn't say anything about it. However, the prime number theorem can also be written as pi of x is asymptotically equal to li of x, where li of x is the offset logarithmic integral function, the integral from 2 to x of 1 over the natural log of t dt. Now, the proofs of the prime number theorem given by Hadamard and Poussin actually show that not only is pi of x asymptotically equal to li of x, but moreover that pi of x is equal to li of x plus an error term, and they were able to give explicit bounds on this error term, in particular on the growth rate of the error term. So the error term does go to infinity as x goes to infinity, but at a controlled rate, and the control was given by Hadamard and Poussin in their proof. Von Koch in 1901 was able to give the best possible bounds on this error term, assuming the Riemann hypothesis is true. Schoenfeld made this precise and proved that the Riemann hypothesis is equivalent to pi of x minus li of x being bounded above by root x times natural logarithm of x over 8 pi. Now, where li of x isn't quite the same as li of x up here. Here's a lowercase l, and that's not a typo. Up here, there's an uppercase l. So lowercase li of x is the unoffset logarithmic integral function. So it's the integral from 0 to x of 1 over ln t dt. And it's related to the offset logarithmic integral function via uppercase li of x is lowercase li of x minus lowercase li of 2. So this result right here is only true if the Riemann hypothesis is true. Moreover, it is equivalent to the Riemann hypothesis. And it tells us a lot about the distribution of prime numbers. The veracity of the Riemann hypothesis, therefore, implies results about the distribution of prime numbers, in particular about how regularly they're distributed, about their expected locations, and how much they cannot vary from their expected locations. So we have reached the end of this course. Let me recap what we have learned. In this course, we've learned about complex numbers, the algebra, geometry, and topology in the complex plane. We learned about complex functions. We studied complex dynamics. We learned about Julia sets of quadratic polynomials. We studied the Mandelbrot set. We even got into the conjecture of local connectedness of the boundary of the Mandelbrot set. We next studied complex differentiation. We learned about the Cauchy-Riemann equations, about analytic functions. We studied conformal mappings, inverse functions, Mobius transformations, even the Riemann mapping theorem. Then we learned about complex integration and about Cauchy theory. So we learned Cauchy's integral theorem and integral formula and their consequences, such as Liouville's theorem, the maximum modulus principle, and so forth. And we finally got to complex series. We studied power series, also called Taylor series, and we even got to the Riemann zeta function and its relation to prime numbers and the Riemann hypothesis. I hope you enjoyed this course.